Okay, this is a continuation of part one. Um, Terminal velocity. When we have an object that is falling, air resistance continues to increase on the object just because as it's falling and increasing its speed, air resistance goes up. Think about moving in a car, and if you stick your hand out of the window when you're going 30 miles an hour, you can feel the air resistance, and if you're going 70 miles an hour, you can feel the air resistance is increased. So what's actually going on is as you continue to speed up as you're falling, air resistance continues to speed up. And there will be a point where the air resistance equals the gravitational force, the weight of the object going down. And at that point, the acceleration of the falling body will terminate. So therefore, at that point, the net force is zero when it stops accelerating, because the air resistance is equal to the object's weight. So the force up equals the force down. And when an object reaches its terminal velocity, it stops accelerating, so it falls then with a constant velocity. And we call that constant velocity its terminal velocity. Terminal meaning that it's stopped accelerating. Okay, its acceleration is terminated. Doesn't mean it's not moving, it's just not accelerating. So let's look at an example here of two guys. One's 100 kilogram, the other one is 200 kilogram, and their air resistance is 100 newtons on each one. So again, I'm going to draw a couple pictures here. This person weighs 100 kilograms, and this person here weighs 200 kilograms. And this is going to show how mass really affects the terminal velocity of an object. So, because it has mass, it's going to have a force due to gravity, otherwise known as its weight, acting down on each guy. And then we have a force upward that's 100 newtons on each guy. So to determine the acceleration, remember, acceleration is equal to the net force over the mass. So we need to find the net force acting on each person. So again, their weights we have to calculate. So let's do that. Weight of this guy is equal to mg. Weight of this guy is equal to mg. So we have a mass of 100 kilograms times 9.80 meters per second squared. So his weight is 980 newtons, where this guy has a weight of 1960 newtons. So you can see that his weight is twice as much because again his mass is twice the mass. So that's the downward force. We have an upward force of 100. So again, to find the net force, it's the forces in the direction of motion, which are down, minus the forces that are opposing motion, which are up. So I plug in my numbers. I'm going to pause the video, see if you can do the same thing for this guy right here and find his net force. Here you see the work. It's the downward force minus the upward force. Again, taking his weight minus the force of friction. And we get a net force of this. I'm going to solve for the acceleration of this guy and then have you do the acceleration of this guy. So let's start here. We have acceleration is equal to the net force. I'm going to take this number and put it right up here. And his mass is 100 kilograms. And we should be able to see in our head that this is going to be 8.80 meters per second squared. So again, you can see that with 100 newtons of air resistance, his acceleration has decreased from 9.8 meters per second squared to 8.8 meters per second squared as he's falling. So again, the air resistance is increased to that value, and you can see that his acceleration has gone down. If it continues to increase, as soon as it gets to 980, you'll see that 980 minus 980, the net force would be 0, so then his acceleration would go to 0. Go ahead and solve for the acceleration of this guy, and then we'll talk a little bit about that. Pause the video and then come back. So here's the work for that part of the problem, and if you notice, his acceleration is slowed too. So he's gone from 9.8 meters per second squared when he initially drops. His air resistance is built up, and he's now going slower. But if you notice, it is a different acceleration rate than the smaller gentleman. So lighter objects are going to reach terminal velocity faster than heavier objects, assuming they have the same surface area. Now, if you have a larger object with a larger surface area, that's not going to hold true. But if they have the same surface area and air resistance value at speed, the heavier object is going to take more air resistance to slow it down, so it's going to be moving faster to build up more air resistance to get it to equal the weight. So again, this only had to reach an air resistance of 980 newtons to slow it to terminal velocity. Or not really slow it, to actually decrease the acceleration until it's 0. And then this one needs 1960 newtons of air resistance to decrease its acceleration to 0. So again, the heavier item or person in this case is going to reach a greater terminal velocity because of that fact. Let's look at Newton's third law, the final law of the three. And this is known as the action-reaction. So if you want to put that right there, action-reaction. So Newton's first law is the law of inertia. Newton's second law is dealing with force and acceleration. And then Newton's third law is dealing with action-reaction forces. So let's look at point 1. Whenever an object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So for example, if I push on the desk, push down on it, the desk is pushing up on my hand. So it's an equal but opposite force. Or if I have a mouse here, if I push on the mouse is pushing back on my finger. So action would be finger on mouse, reaction mouse on finger. So let's look at this one here. It says when a bullet is fired from a gun, you have equal and opposite forces acting on the bullet and gun. However, they have different motions as a result of that force. The bullet will have a greater acceleration because of its smaller mass. So this is where we have to take into account Newton's second law. So Newton's second law said the acceleration is equal to a net force over the mass. So if we have equal forces acting on a bullet and a gun, but we decrease the mass, so if we make that number very small, what's the acceleration going to do? The acceleration is going to get very big as a result. So that's why the gun, even though it accelerates backward, it's at a slower acceleration rate than the bullet going forward, and because the mass of the gun is so heavy. If you've ever fired a shotgun before, you're thankful for this because you wouldn't have an arm if this were not true. The gun would accelerate through your arm and rip your arm off. But it doesn't. It goes back. It does kick back into your shoulder, but the acceleration is not nearly as the same as the bullet that's moving forward as it accelerates through the barrel. So let's look at number 3. It says when you kick a football, you exert an action force on the football in turn exerts an equal but opposite reaction force on your foot. So why don't they cancel? Well, I'm going to draw a picture to kind of explain this to you, which I think will help. This is a common misconception for a lot of students. Now, excuse my drawings here, they're going to be really blocky. There's my football. Yes, I know, it looks great. And here's the foot. Lovely. So when the foot kicks the football, there's a net force acting on the football in this direction. So what does the football do? Well, net force produces an acceleration, so it accelerates this way. to the right. The foot has a net force acting on it in this direction. This is your action-reaction pair when they collide together. So what does the foot do? Well, the foot was moving with an initial velocity, right? When it hits the football, what does the foot do? Well, the velocity is in this direction to the right, and the net force is opposing it. So the foot slows as it kicks through the ball. And that should make sense. But these forces do not cancel each other. That's what most people would say, is that the forces cancel each other. They do not. The reason why they do not is because they're acting on two different objects. The only force acting on the football is this one here from the foot. The only force acting on the foot is this one here, which is from the ball. This speeds up as it goes this way. This had an initial velocity when it hit the ball, and now it slows down as it's swinging through. Now, what if we are playing soccer, let's say, and we have another person here, and this person kicks the ball as hard as this person does? Well, its foot has a force on the ball in this direction, and the ball has a force on his foot in this direction. Now look at the forces acting on the ball. What is the net force of these two forces acting on the ball? Well, here the net force is 0 newtons if these are equal values. These forces cancel each other out. So what does the ball do? It stays put. What does this leg do? It slows down and stops on the ball here. What does this leg do? Slows down and stops on the ball here. So both these players' legs get hurt and the ball stays put. If you've ever played soccer, this is a common occurrence, especially with little kids. They both go up to kick the ball, they both kick it, the ball doesn't move, and the players fall down and their legs hurt. That's what happens when my sons play soccer. But anyway, that's what's going on. These forces cancel each other out on the soccer ball. It does not accelerate, therefore it does not change its motion. These legs were moving with the velocity, and all of a sudden their velocity goes to 0, so they have a negative acceleration on them, so they slow down. I hope that's fairly clear on that. Those are some common misconceptions on what's going on. We'll talk about another one in class on Monday. Let's get back to the note sheet and finish up. So let's look here. Number 4. It says, at one time it was believed that rockets could not be fired into outer space because there would be no air for the gas to press on it. They actually work better in space because there's no air resistance to slow it down. So how do rockets fly? Well, here's again a common misconception. Again, let me draw another picture for you. Okay, so let's take a look at this rocket here. Again, it's sitting here, and how does it actually accelerate upward? Well, most people say that it pushes on air. That's not entirely true. It's not actually true at all. What's actually happening is that there are exhaust fumes that it's pushing out of here. So there's an internal explosion going on, and it's blowing out exhaust, and that exhaust actually has mass. So what's happening is that the rocket is pushing on these little exhaust particles and accelerating them, so giving them a force and pushing downward on them. Well, if the exhaust is being pushed downward, then by the rocket, what is the exhaust doing back on the rocket? Well, the exhaust pushes back on the rocket, and it pushes upward on the rocket. So if you think about how much exhaust it takes to shoot out of the bottom here in order for this very massive rocket to start to accelerate. That's why there's this huge cloud of smoke around a launch pad, because the billions and trillions and numbers of moles of molecules being forced from the exhaust here to get this to accelerate up. You can also think of it this way. If you had a pole and if you had a gun, a machine gun, attached to a pole, let's say, well, every time I fire a bullet, The bullet comes out, and what does the gun do? It accelerates